Next speakers are Renzo and Marzieh. So Marzieh will take over from Renzo then online, and they have been working on biology-driven whole genome sequence genomic predictions for feed efficiency within and across breeds. Renzo, please.
Thank you, Birgit. Hi, everyone. So this presentation we will split in half. I will introduce you to the first part of this work, which we conducted together with the people that you see listed here, and mostly between Wageningen and University of Alberta. So I will show you the results within each country, analysis independent, and then Marzieh will continue with some investigations she did on the Canadian data set and also on the status of the across country. So, as Emre said, with whole genome sequence data, we have access to millions of variants, but we really need to pinpoint the causal one to make it work. So this is especially important if we look at biologically efficiency traits, such as feed efficiency in cattle. So within WUR, now with this catalog of functionally genomic features, we could just use them to do some SNP prioritization and then include this information into biology-driven genomic predictions. So this is what we did here. We validated within and across breed biology-driven genomic predictions for dry matter intake using WUR genomic features. And this is an overview of the data set available. From the Netherlands, we had dairy Holstein, and from Canada, beef crosses. From the Netherlands, we have the regress proofs as dependent variables, and from Canada, pre-corrected DMI. Then you can see also that the Canadian dataset is a bit larger with about 5,500 cows and bulls, so individual data, while from the Netherlands, 3,000 cows. Then we estimated accuracy and bias using a forward-in-time validation approach, which will mimic the breeding application, and imputed the 50K genotypes up to whole genome sequence using Beagle, and then proceeded with the SNP prioritization of variants. In terms of genomic features, we focus on using those of WUR from WUR package 4, from QTL and eQTL, and WUR package 2 ATAC-seq information. So you can see here all the traits and tissues we included. We started off by using everything, so without making specific selection, as the trait is a bit complex and could be influenced both by things like, as you can see, for instance, for QTL, feed efficiency itself, but also for other correlated traits related instead more to the production of the breed. For ATAC-seq, Gabriel produced for us also ATAC-seq consensus peaks, so we also have used those. Then a big chunk of work was conducted at the University of Alberta by Lael and Paul Stothart, and what they did was to make it easier for us to access genomic features. They mapped them all from the WUR database, all to the 1,000 bull genome variants. And in this way, we could have quick access to the position, the interval, or p-values that were available for this, from this project. Then we could select the genomic feature group that we want to work. As I mentioned before, we just took all traits and all tissues, exclude the variants that are not in our 50K commercial chip or within each country whole genome sequence, and proceed with some clamping to reduce the number of variants that we carry into the genomic selection. And finally, extract the biallelic ones to model as SNPs on top of a 50K layer. So we use the approach that Emre mentioned before. So these are the scenarios we put in place using the software NextGP, so Emre's software. In the 50K scenario, you can see the number of SNPs for the Netherlands and Canada. And here we use a SNP lab approach, so we have a common variance across all SNPs. Then on top of this 50K, we add SNPs that has been prioritized for QTL only or eQTLs. And you can see also, again, the number of SNPs that we add on top of each country 50K chip. And finally, we combine them all using QTL, eQTL, and then also including the information, whereas a variant is in an ATAC-seq interval or out. For the additional genomic features layer, we tried both SNP lab and Bayesian approach, where we basically say that one group of SNPs can explain a larger proportion of variants, and another one has explained almost no variants, but we saw there was no advantage of the Bayesian model over a simple SNP lab. And finally, for the last layer, we basically have the possibility that some variants overlap, as Emre explained. So, for instance, a variant can be QTL and or EQTL and or present or absent in an attack-seq interval. So, for instance, in the Dutch dataset, 57% of them were within an attack interval. And here we use a biased RCPI approach by using 2 classes instead of the proposed 4, simply because convergence was better with 2 classes. So into the results for the Netherlands, here you see on the x-axis all the scenarios tested. On the first column, you see for the 50K, we start off with an accuracy of about 0.43. And then the green line represents what we want to beat once we add SNPs that have been prioritized from genomic futures. And you can see that if we add QTL or EQTL on top of it, or if we go with attack-seq information in the multi-genomic futures layer, we really don't improve much. So those boxes at the top are the relative increase compared to the 50K scenario, and you can see that it's not significantly higher. And also there was no impact on dispersion. So overall, for the Netherlands, we didn't see an improvement. From the Canadian point of view instead, so on their dataset, what we saw is slightly different. So we start off from a lower accuracy to start with on the 50K scenario. This is likely due to the fact that it's a more heterogeneous dataset. We have more breeds, and we have both male and females. So we have about 0.24 as a starting accuracy. And you can see that while for EQTL we don't get any improvement, for QTL instead, we do have a 24% increase, relative increase to the 50K. Now, already the QTL layer, which you can see fitted alone, already gave quite good accuracies. And then we further improve slightly if we also include information on where variants are in or out of an attack-seq interval. Similar pattern was also obtained for dispersion. So if the accuracy improved, also dispersion improved. And so now Marzieh will continue on some investigations that we did for these specific results on the QTLs.
Okay, thank you, Renzo. I'm sorry for my camera that's not working. Hello, everybody. My name is Marzieh, and I'm a research associate at the University of Alberta. So I'll continue with the presentation of Renzo. So as Renzo showed, for the Canadian data, we had the improvement in prediction accuracy when we added the QTL on top of the 50K. So here in this slide, you see the 3 GWAS plots for beef and dairy and combined data set. So for the beef data that I worked with, you can see this is the GWAS results are from work package 4. So you can see that on 3 chromosomes, 6, 14, and 20, there was like a significant GWAS peaks that was observed. So what we did is just like to validate if these peaks of GWAS has also, I mean, the SNPs on these peaks has also the big SNP variance from the prediction model. So in the table below, you can see that, for example, for the chromosome 6, 14, and 20 that are highlighted in red, those SNPs has also the SNP variance, which is larger than other SNP variants for other SNPs. So, however, we can see also that on chromosomes 2 and 5, there are like several SNPs with big variants. But this could be because like when we added the QTL on top of 50K, it's not only the QTL for dry matter intake, it's QTL from other traits. That's why the large SNP variances from chromosome 2 and 5 could be because of the significant peaks from other traits than the dry matter intake. And next slide, please. So in this slide, I want to show some of the results of the crossbreed genomic predictions. In this plot, we just plotted the correlation between the SNP effects from the Canadian data and the Netherlands data. You can see that the correlation is basically 0, but we still tested the prediction accuracy, even though we knew that it could be close to 0, the prediction accuracy, when the correlation between SNP effects of the 2 data sets are 0. So in this table, you can see that we tested 5 scenarios, and then the SNP effects from the Netherlands data was used to do the prediction in Canadian data set. So you can see in the last column, the prediction is basically, the accuracy is 0. So the next step that Renzo will try is just multi-breed Netherlands and Canadian data. It means he will combine the training population from both populations, and from Canadian and Netherlands data, to do the prediction for either of the populations. And next slide, please. So we also tried to add ATAC-seq on top of 50K, and the way that we selected the ATAC-seq varies. We tried probably more than 40 scenarios of different ways of ATAC-seq selections, but here in this slide I present only 4 of them, 4 of the scenarios that we have tried. So the ATAC-seq ratio is include the variance, the top 10K variance from the ATAC-seq narrow peaks. So it's basically the ratio of the overlaps in selected tissues that are highlighted in red here over the overlaps in all tissues. So we ended up more than 200,000 SNPs, and because it was large number of SNPs, as Emre indicated for the program, so we did LD pruning on these SNPs. So we ended up more than 19,000 SNPs at the genome as a genomic feature layer. And for the ATAC-seq housekeep scenario, those include the top 10K variants that overlaps across all narrow peaks. And the ATAC-seq random are just the random selection of ATAC-seq, and the ATAC-seq weights is a scenario where the variance is scored, and is an equation that is used to score the variance, so that the higher weights that are on less frequent variants, such as QTL. Sorry, for the first scenario, ATAC-seq ratio, I forgot to say that we also, besides the top 10K variants, we also added adjacent SNPs, 200 kb upstream and downstream. Next slide, please. So this is the results of ATAC-seq. So as you can see, I mean, it's hardly, compared to the 50K, it's hardly improved the prediction accuracy when we tried different way of ATAC-seq selection. And the model that has been used to generate these results is a SNP blob model. And for the random selected variants in the green bar, as you can see, is either the same or higher accuracy compared to the rest of the scenarios. So something else that could be done, or we will do it, is just like adding those 4 layers of ATAC-seq in as one genomic features and run a new model to see how it will be, the result will be when we combine all of them. And next slide, please. So here is the results of a base LV. Base LV is basically a model that can accept the 0-1 code and p-values as well. As Emre showed, and he tried the 0-1 code, we tried both. We tried, like in the genomic feature layer, the 0-1 code and p-values to see what's the difference in the results. As you can see, the prediction accuracy results really didn't differ. I mean, if we add like 0-1 code or p-value into the genomic feature layer, and for the dispersion or bias results, also you can see between the two way of coding, I mean, either p-value or 0-1 code, the results didn't change, but however, it's lower than 50K. And next slide, please. So in conclusion, we concluded that inclusion of genomic features could increase genomic prediction accuracies for dry matter intake, as you notice for the Canadian data. However, the results may vary across different data sets, because for the Dutch data, we basically didn't see any improvement or little improvement. And in terms of the model, different models we tried, the Bayesian and SNP blob really didn't differ in terms of prediction accuracy. So finally, next slide, please. I would like to acknowledge the WUR Consortium for providing the genomic features data. And also, next slide, please, and its partners, especially University of Alberta and Wageningen University, for providing the genotypic data and the phenotypic data. And thank you all for your attention.
Thank you very much, Renzo and Marzieh. Maybe we have one question. We have an online. Why do you think that the addition of further features does not have as much benefit as expected? Is it a matter of a lack of true information, or is it a matter of not yet having the most efficient models?
That's a good
Can I
question. Marzieh, do you want to take this?
Yeah, I have some ideas. I'm not sure if it's the best answer, but I think it can be both actually. Because like the way that, for example, for ATAC-seq, we had millions of variants. The way that we selected them could be like, of course, we tried many scenarios, but the way that we did do selection on those millions of variants couldn't be the best like way of selection. So that's why we can say this could be due to not lack of information, not, I wouldn't say lack of information, I would say it's because of not selecting the best way of selection, variant selection. And also the modeling, I think it's Emre's expertise to answer this question, but it could be the models as well.
Emre, would you like to comment, or? Yeah.
Could be both. If we accept that the data is not accurate enough, I mean the earlier findings, then of course we should squeeze it a little bit and try to develop models that can get the most out of it. But it's always both. And actually, what you have to deal with in data science is actually try to get the most out of whatever data you have. So it's both, anyways.
Yeah. One from Didier, and then one online, and then.
It's more a comment than a question. Probably the validation population we use is not the right one. At the first generation, nearly all the models provide equivalent results, not exactly in the same way, but with the same accuracy. But as shown by Redong a while ago, this morning, if we choose validation 2 or 3 generation later, or in another unrelated or little related population, we may observe a superiority of the model with annotation, because the erosion of the effect will be smaller and the estimates more robust. At least I hope so. That's a feeling. It would be good to test that, I guess.
Yeah, I agree. Unfortunately, I think both data sets are not good to fit for this purpose. Yeah, we don't have enough generations to do that. Yeah.
We have one online question from Gutam. Did you have the same cows both for GWAS and genomic prediction?
So the discovery data set was not the genomic prediction training, if that's the question. No, so the answer is no.
Can I add something? For the Canadian data set, we also didn't have the overlaps. It was just a few overlaps that it was excluded between the genomic prediction and GWAS data.
Yeah, but for Holstein, we specifically looked at this, that
Yeah.
GWAS was done without the Holstein data set, and then not to mix up.
Jose Espinosa from CRG. So if I understood it correctly, the Canadian data set was more heterogeneous, right? Yeah. So could it be that in a situation where you have more noise, actually the genomic features help to rescue the true signal?
Could be. Or they just, you can improve only what is not already at a good level. But yeah, that could be. But then which genomic features are the most? I mean, QTL seems to be the only one that adds really something to it. Yeah.
Good. Well,
yeah.
Thank you very much, Renzo and Marzieh. We move on to the next speaker.